After having studied the law of conservation of momentum, let's talk about its applications. When a gun is loaded with the bullet is fired. The bullet moves with a very high velocity. By Newton's third law, to every action there is equal and opposite reaction. Thus, gun recoils in the opposite direction. Since gun is much more massive than the bullet, it recoils back with very less velocity. Here, the mass of the gun is denoted by capital M, and mass of bullet is denoted by small m. As the gun is fired, the bullet moves forward with velocity of small v. As a result, the gun recoils back with velocity capital V. Now, according to the law of conservation of momentum, the total momentum before firing is equal to the total momentum after firing, that is, the initial momentum is equal to final momentum. Now, the initial momentum of the system is 0 because initially the gun and the bullet both were in a position of rest. Talking about the final momentum of the system after firing, so we can say it is equal to the momentum of bullet plus the momentum of the gun, that is small mv plus capital MV. Now if we rearrange the equation we'll get the recoil velocity of the gun as minus mv upon capital M. Here the negative sign shows that the direction of recoil of gun is opposite to the direction of velocity of the bullet, so we can say the recoil velocity of bullet is opposite to the direction of motion of the bullet. The rocket works on the principle of law of conservation of momentum. The gases ejected from the nozzle gives a force upwards to the rocket. We can also apply law of conservation of momentum in case of rocket repulsion. If we ignore external forces, the momentum gained by the rocket in the forward direction is equal in magnitude the momentum of gases in the opposite direction. Thus the rocket and the exhaust gases push one another, and Newton's third law of motion is applicable in this case. Suppose the gases are ejected at a velocity of small v, and masses of fuel gases is denoted by small m. The mass of rocket is denoted by capital M, and it moves forward with the velocity of capital V. Now, according to the law of conservation of momentum, we know the initial momentum is equal to final momentum. Now initial momentum of rocket can be stated as mass into velocity. Initially the rocket was at rest, so its velocity was 0. So we can write the initial momentum of rocket is m into 0, that is 0. If we talk about the initial momentum of the fuel, initially the fuel was also at rest position. So we can say the mass into velocity of fuel, that is again 0, so initially momentum of fuel can be given as m into 0, that is again 0. If we talk about the initial momentum, that is total initial momentum, we can say it as sum of initial momentum of rocket plus initial momentum of fuel. The both are 0, so the total initial momentum is also 0. Now, final momentum of rocket when the velocity v is being acquired by the rocket. So we can say if we talk about the final momentum of rocket, we can say it as mass into final velocity of rocket, that is m into capital V. If we talk about final momentum of fuel, the mass of fuel is small m and velocity is small v. So final momentum of fuel can be given as mv. The total final momentum of the system, now it's given by sum of final momentum of rocket and final momentum of fuel, so we can say the total final momentum is equal to mv plus small mv, which gives us the total final momentum of the system. Now, if we equate, or if we substitute the values of total initial momentum and final momentum in this expression, we can say the initial momentum is equal to the total final momentum. If we rewrite the equation by more simplifying it, we can write the velocity of rocket that we denoted by capital V is equal to minus of small mv upon capital M. Here this negative sign denotes that the direction of velocity of rocket is opposite to the direction of motion of gas. So this is same the expression that we have already derived in case of motion of gun, or say required velocity of gun.